Welcome to the second part of Unit 2, and in this second part we are going to encounter the first vectors and scalars of our physics course. And that first vector is the position vector. Position is the location of an object within your coordinate system. So now imagine that you're standing on a corner in Shepherdstown. Somebody comes up to you and asks, "Hey, where's the library?" Well, the first thing you have to do is probably clarify which library they mean. Do they mean the town library or the university library? And then you would tell them what to do. You would tell them, hey, it's one block down that way or one block the other way. What you've just done is describe the location of the library in a coordinate system with you at its center, right? The location of an object within your coordinate system. Had you been standing on a different corner and asked the same question, then your answer would have changed, even though the library isn't physically moving. So now let's see how that works, right? So I'm going to define a simple one-dimensional coordinate system. Here you go. And the first thing I'm going to do is I'm going to put whatever that object is right where I'm standing. So it's at the 0 location. Because it's position and we're looking at locations, the units here are meters. So now I could look at, say, 3 meters to this side and 3 meters to that side. Position of that object in this coordinate system is 0 meters. Okay, now I'm going to erase that coordinate system. And now I'm going to find a new coordinate system. I'll again let the positive direction be this way, but now I'm going to put 0 over here. So 1, 2, 3, 4. So in this coordinate system, that object, which didn't move, it's in the exact same position on that page, is now at 4 meters. Position of an object depends on the coordinate system. Displacement, on the other hand, does not depend on the coordinate system, and I will illustrate this as well. So displacement, by definition, is the change in position. So really quick, before we get into examples, let's write this down. Here is how you calculate a displacement, a change in position. And you're going, oh my. Okay, so first things first. Change in. Anytime you see the words change in, you should expect to see this little triangle. That little triangle is known as delta because it is the Greek letter delta. And every time you see a delta, you think change in. X is one of the variables commonly used to represent a position. So delta X means change in position. Okay. Now there's a little arrow over the top. That little arrow over the top is just a reminder, hey, it's a vector. So watch out for directions. Okay, so displacement, change in position, delta x, equals the final position minus the initial position. That is the definition. Okay, so down here I have our friend the green dot, and you can see it's changing position. It started here, start, and it finished there. So its initial position is where it was up here, and its final position is where it is down below. Okay. And now I'm going to define a coordinate system that goes straight between these two. Okay. And let's let 0 be where it started, and let's let 5 meters be where it ends. Fair enough? And notice that means that the positive direction is going down and to the right. Okay, using my definition of displacement, I'm going to take my final position, which is at 5 meters, subtract off my initial position, which is 0 meters, and that gives me a change in position of 5 meters. Okay. Now I'm going to shift the coordinate system. I'm going to still let positive be to the down and to the right, but I'm going to move the origin. Okay. So now let's move the origin so that it's back over here off the coordinate system, and let's let this be the 10-meter mark, and preserving the scale, that means this one's 5 meters away, so this is now at 15 meters mark. In this new coordinate system, I'll go down here for the new coordinate system, delta x is going to be 15 meters. the final position, minus the initial position of 10 meters, and again, I get an answer out of 5 meters. So while the positions have changed, as long as I've preserved the orientation of my coordinate system and the scale of my coordinate system, I get the same displacement out. Now, if I had rescaled the coordinate system, I would have to do a conversion between one scale and the other, and I could still get the same distance out. But now what happens if I rotate the coordinate system? Instead of working in that red one, I'm going to draw a new coordinate system that has positive going the other way. So now let's let positive be up and to the left. And because positive is that way, I'm going to let the initial position be 15, the final position be 10, which means 0 is down that way, which does give me positive going up and to the left. In this coordinate system, my final position is 10 meters, my initial position is 15 meters, and I get a displacement of negative 5 meters. Well, the number is the same. The magnitude of the displacement is the same. I get 5 meters either direction, but now I have a minus sign that's different. That minus sign is telling me about direction. And anytime you see a positive or a negative sign associated with a vector quantity, you should think, that's telling me about direction. When I was working in the red coordinate system, the motion of this green dot was in the positive direction of my red coordinate system. And that's why the number in both the red cases came out to be a positive 5 meters. In the green coordinate system, the motion of the object is now in the negative direction because I flipped around which direction was positive. And this negative sign is telling me, hey, it's going in the negative direction. As long as I interpret that answer in the coordinate system, I still get the same result. Okay. So I'll reiterate what I said in part 1. Make your choice, be self-consistent, interpret within your choice, and you can get it right, assuming you do everything there correctly. Okay. Now, you may be wondering, well, we're talking about distances, right? And the answer is no, we're not talking about distances. We're talking about displacements. Distance is not the same thing as a displacement. Notice with displacement, all that matters is where it starts and where it stops. And there's no comment at all in that calculation about how it got from point 1 to point 2. Distance is a scalar, usually represented by the letter d. It cares about path, right? So if I start here and end there, using the coordinate systems I had in the previous slide, so if I let this be 5 meters, let this be 0 meters, I believe this was the first one I drew in red on the previous slide, with positive down and to the right. The displacement here again is 5 meters, a positive 5 meters. Okay. How did the particle get from here to there? Did it go out and around like this? Well, that's going to be one distance. Did it follow the straight line path? Well, that'd be a different distance. Maybe it did something even different. Maybe it did curlicues along the way. I don't know. That would be yet another distance traveled. And each one of those compares about how long, let's try again. Each one of those options cares about how long the path was. Let me give you one more example. Think about starting in Shepherdstown and trying to drive to the Green Bank Observatory, right? I can grab a map, right? I could sit down with my map, connect the dot between Shepherdstown and Green Bank, measure that line, and in the scale determine how far apart those were. And that length along the straight line connecting them, or as the crow flies, or how an airplane would potentially go, that is the size of the displacement. Okay? But if I'm going to drive from Shepherdstown to Green Bank, I can't drive on that straight line path. One, there's no roads. Two, even if there was a road, it's got to go around the mountains or up and over the mountains. And so to get there, that matters. And the distance to go from Shepherdstown to Greenbank would most likely exceed the displacement between those two. I can't think of how it would not exceed it. I could think, possibly it being equal if it was straight and flat and all of that, but it's not between Shepherdstown and Greenbank. Okay. So on that note, let's ask a couple of questions to finish up. Can the distance an object traveled be 0 while the displacement is non-zero? Okay, well, think about this. What does it take for the distance an object traveled to be 0? Well, if I've traveled a distance of 0, that means I've not gone anywhere. The length of my path is 0. And if I've not gone anywhere, then my initial and final positions have to be the same, in which case my displacement is also 0. So the answer to the first question is no. Can the distance an object traveled be 0 while the displacement is non-zero? No. In order to have a displacement that is non-zero, I have to have gone somewhere, in which case distance is going to not be 0. Now let's look at the reverse of that question. Can the displacement be 0 while the distance is non-zero? And the answer here is yes. Okay, so let me give you an example to illustrate. Let's say that you start right here and you go out, you go around, and you come back and you stop at exactly that same spot. Well, now my final and initial positions are the same, so my displacement is 0. Can the displacement be 0? Yes. Final and initial positions are the same, displacement is 0. Did I travel a non-zero distance? Yes. Okay, an example of this is any round trip. So it might be that you go out, you run a lap on the track, start and stop at the same spot. It might be chasing somebody around the house or around the car or whatever. As long as you start and stop in the same location, your displacement will be 0 and the distance you travel will be non-zero. That concludes part 2. In part 3, we're going to look at speed and velocity.